Very quick video here to make sure that you understand sigma notation for summation. We use this sometimes in algorithmics for sequences. I don't know that it's going to be tested, but you should know this anyway as general mathematical background. So it's kind of like a for loop, something like for I equals 1 to 5, add 3i plus 4 is how we're going to read this. And so just like in a for loop, we let I equal 1, it gives us a result. Then we let I equal 2, gives us 10, and so on, and so on, and so on. And we add the numbers together, and we get our result. Easy peasy. If you were to somehow get one of these in an algorithmics exam, and it would be in some sort of context, it's not going to be a straight question, I would write out the first few. Now notice here this one starts at 5, so we've got 5 plus 30 as the first term, plus 5 plus, so 6 times 6 is 36. That should be enough. We'll just write another one. So 7, I is now 7. 6 times 7 is 42 plus 5. We add those together. We've got 35 plus 41 plus 47. And we can see those are going up in sixes. So that suggests A, we've done it right. B, we've got an arithmetic sequence where U1 equals 35, D equals 6. And how many terms are there? This is quite easy to stuff up. It's actually going to be, so I equals 5, 6, 7, 8, 9, 10. That was 6 terms, plus another 10 to get to 20. So n equals 16 in this case. And then we would say that the sum of those terms, Sn equals n over 2, 2u1 plus n minus 1 d. Hopefully this is not a complete shock to you, this particular formula, but if it is, probably don't learn it for specialist maths, giving us 1280. 1, 2, 8, 0. Pause and try the next one if this is something you want to crack. So we've got 10 minus 2, which is 8, and then 6, and then 4. We can see u1 equals 8, d equals negative 2, n equals 20, Sn equals 20 over 2, 2 lots of u1s, that's 16, plus 19 times negative 2. That one's a bit more gentle, isn't it? Yes, negative 220. Now, some other interesting results that can very occasionally come up. If we have this one here, it's pretty easy to illustrate these through examples. So if I have the sum from I equals 2 to 7 of 3i, because that's going to be 3 times a bunch of i's, we can take the 3 out, essentially. Not much of an explanation, but hopefully convincing enough. And that can make it simpler for reasons you will see. For the next result, the thing we're adding, the k, actually doesn't care about the counter. So when I equals 1, k is k. When I equals 2, k is k. When I equals 3, k is k. And we're doing that n times. So if we had the sum I equals 1 to 20 of 2, that is going to be 2 times 20, which is 40. And the last identity down here is just a useful tool for finding the sum of the first n natural numbers. Sort of thing that comes up in primary school investigations back in the day. So if we wanted to find the sum of the first 10 numbers, I equals 1 to 10 of I, we do 10 times 11 over 2, which is 55. And you can check that if you want. 1 plus 2 plus 3 plus 4 plus 5, etc. up to 10.